last time I showed you an example which I tried to where I tried to plot the solid which is enclosed by two surfaces, but since I was not sure how to do it with Maple, and I didn't want to spend time to figure out how to do it, so I want to discuss this example maybe once more, just to show you today, because I just prepared it, so I just checked it how to do it. So let's once more look at the example. We have two quadratic surfaces. So this one z is equal to x squared plus y squared, and we have another one, this one. Okay, so from our classification of quadratic surfaces, we know that so this is a quadratic surface, and you see that the cross sections. If you fix x, you get a parabola. If you fix y, you get a parabola. So this is a paraboloid, and if you fix z, what you get is in this case circles. But if you replace, if you have here general coefficients, then what you get are ellipse. So this surface, this quadratic surface, according to our classification we have learned last time, is an elliptic paraboloid, and this as well. Okay, so both of them are elliptic paraboloids, and last time we discussed how to plot the solid which is enclosed by those two here using Maple. Now, last time I showed you, what you're going to do is, because the equations are getting more simple if you introduce cylindrical coordinates. So in cylindrical coordinates, this equation reads z is equal to r squared, and this equation becomes z is equal to 5 minus r squared, and you have to figure out what is the range over which you have to plot it. So if we make already, this is something which is, I do not need the coordinate system. This is something which is not so hard to visualize. So you have one solid, one surface which looks like this here, and then you have the other one on the top of it. So you have something like this here. Now, what we have to compute is, the range over which we are going to plot the two surfaces. So last time I showed you already, so you just equate those two and you get that r is equal to square root of 5/2. Of course, you have two solutions, but you can neglect the negative one. So if you plot those two here over the range r from 0 to square root of 5/2, then you should get a plot of the solid which is enclosed by those two surfaces. Now, I tried to do this last time with Maple. Maybe you remember it, but I failed to do it. The reason being that if you use this usual plot 3D command of Maple, so this one, of course you can plot here. Using this one, you can plot surfaces which are given in cylindrical coordinates. You just have to add the coordinate specifier. Coordinates is equal to cylindrical. But if you look at the help, last time we saw already that this is plot 3D, and then what was the plot options? Okay, so you see that if you look here at, you have a comment, where is it, which is called coordinates, this one. This is the coordinate system. Wait a moment. This maybe plot 3D. You see, yeah, I have to check this one, plot 3D coordinates. so you see here that if you use the plot 3D command in order to plot a curve which is given in a surface, sorry, which is given in cylindrical coordinates, you see you always have to check, okay, what is the syntax? So you see here that if you use cylindrical coordinates, then what Maples requires is not, here we have set as a function of r and theta, but what Maple requires is that the expression, the meaning of the expression is r is a function of theta and z. Okay, so this wouldn't be a problem for the first one, so you just solve it for z, then you have r is equal to the square root of z. And because of this range here, you see that z must be equal from 0 to 5/2. So you can actually use the plot 3D command to plot this curve here. So plot 3D. Now our curve is square root of z. Now theta is from 0 to, you do not see any theta, so theta is from 0 to 2 pi. The z is from 0 to 5/2. And the coordinates, you have to tell Maple that the coordinates which you use are cylindrical. Okay, so you see this is the, of course this just gives you one part, this gives you just the lower part of the solid which you want to plot. Okay. Last time I tried to do this, so if you remember, but I wrote those two here, theta and z in the different order. Okay, I first wrote z and then theta, but so you also have to be careful here about the order. Okay, because Maple expects that no matter how you name the variables, okay, Maple expects that the first range is for theta and the second range is for z. So if you interchange this, then you get a different picture. Okay, like if you plot a function of two variables, x and y, then the first one is always x, the second one is y. Otherwise, you get the curve different. So that was the mistake last time. Now, the problem is if I plot those two surfaces, because I can now express this as well as a function of z, then I have here 5 minus z. But you see the problem is that the range here for z will be different. Okay, so here because if you plug this in, you see z goes from 5/2 to 5. Okay, now this is not very convenient because this means I cannot plot it in the same window. Okay, because I cannot if I specify the set range from 0 to 5, okay, I must tell Maple, okay, for this range use this function, for this range use this function. Okay, but this is not so easy using the plot 3D command. Okay, so actually by expressing those two functions here like this, it's not possible, easily possible to plot it in the same window. Okay, I could plot it, of course, in a different plotting window, but this is not what I want. I want to see the whole. I want to plot the solid of the two surfaces, which is enclosed by the two surfaces. Now, a better option is using the implicit plot command. Okay, because for the implicit plot command, the difference is if you use plot 3D, okay, then you can just specify two of the three possible ranges. Okay, you can just specify z and theta as you see here. Okay, and the r then will be determined by those two. Okay, but if you use the implicit plot, you can specify all three ranges. Okay, so you have more freedom in order to plot something like this. So for this, I would suggest to use the implicit plot command, and this is actually not standard in Maple, so you have to load in this new command. So you see with plots, you get a couple of new commands, and one of them is implicit plot 3D, which is where? Over there, implicit plot 3D. Okay, so we wanna plot now again. We have implicit plot 3D. Now we wanna really plot this solid here. Okay, so the solid which is enclosed by those two surfaces. okay, so first for the first one, okay, we can of course write it now in this form. So z is equal to r square, and now I have to specify the range of z, r, and theta, okay. But again, the order is important, okay. The order in which Maple interprets whether this is z, r, or theta. So I have to check the order in which I have to write those three. I'm not sure. I always forget it. I'm not sure whether it's r theta, r z theta, or r theta z. I'm never sure. So before I do this, okay. So forget about this. Let's erase this. Let's check how the order is. You see, here's an example. Most of the time I just look at the example because I'm too lazy to read what is written here. So I just look at the example. You see here's an example with cylindrical coordinates. And you see the first one, the first range must be for r, the second for theta, and the last one for z. Okay, so r, theta, z is the order. Of course, if you change the order, okay, Maple will plot a completely different surface. So r, theta, and z is the order. Okay, so now we plot. Now we plot the first one. The first is z is equal to r square. So the r we already determined here. The r goes from 0 to square root of 5/2. The theta goes from 0 to 2 pi. And for the z, okay, so if I look at this range, so from 0 to 5/2. And I have to tell Maple that the coordinates are cylindrical. Okay, so first let's. Okay, so this is the one. You see, if you use implicit plot, the plot is not so nice compared to plot 3D. Okay, the reason being because it's more complicated. Okay, because what Maple is essentially doing is Maple is choosing a grid and computing the value just for points at the grid and then interpolating between them. Okay, so you see, it doesn't look so nice. If you do not like this picture, if you think it has too much, it is not smooth enough. Okay, then you can. Tell Maple use more points. So make the grid larger. For instance, this one. Okay. So now a different grid. So you see now the grid is much finer. So the computation is done for much more points. Okay. So now the advantage of the implicit plot 3D comment is okay. So if I here you see I have here 3 ranges. I have the freedom to choose the 3 ranges. Okay. If I extend the range for z, okay, for instance up to 5, if I extend the range of z, because the range for theta and r are already fixed, okay, nothing will happen, okay, because the range for r and the range for theta are dependent, okay. So if I do this, then nothing will happen. Okay, so it's the same. It's the same actually. Where is it? It's the same actually. Just the upper part is left empty. Okay, because the reason is because the r is not changing. I haven't changed the r. I have just changed the z. So you get the same solid. Okay, just the upper part is empty, and that's what I want because I want to fill the upper part with the other solid. Okay, so now I just I plot 2 of them. If you plot 2 of them, you have to enclose them in such brackets. Okay, so the other one is 5 minus r squared, and the range is already correct. Okay, now you see that's what I wanted. Okay, so you see that using Maple, it's not always, you have to think a little bit about how to plot something like this. Okay, if you use the usual plot 3D command, it wouldn't be possible to to plot a solid, okay, because the ranges are different if you go along set, okay. And even if you use the implicit 3D comment, you have to think about what are the right ranges that you get the right plot, okay. But the essential thing I want to say, the message is that implicit plot 3D is like the better comment in the sense that you have more freedom in choosing the ranges, because you can specify all three ranges, okay. Whereas if you use the plot 3D comment, one range will be dependent on the others, and you do not have any possibility to choose it. Because actually this example, I have it from the textbook, and I checked the solution manual. The solution manual claims you can plot it like this, and with this range with Maple. It's not possible, because Maple interprets a function in cylindrical coordinates different. So you indeed have to use the implicit plot 3D comment. Okay, so here you see how to use Maple in order to plot something like this. Maybe I will assign some of the in the forthcoming homework for the forthcoming assignments. I will assign some exercises where you have also to use Maple to plot something. If I give you such an exercise, the only thing you have to do is you have to plot it and you print this out and handle it in with your homework paper. And of course, you also print. The most important thing is to print this over there, okay, which the comments you used, okay. So what I want to see is more or less. Actually, another way is you do not have to print it out, but you just give me the comment, okay, with which the required solid can be plotted. And you see, sometimes you have to think a little bit you have to think a little bit in order to come up with the right ranges over which you plot the solid here in this case. Okay, so any questions to this? Actually, if you do not like the way Maple is plotting this solid, you can do all kinds of changes. For instance, you can tell Maple to use a different style. So if you do not like the grid, you can take away the grid. So you can something like batch no grid. Okay, then you get it like this here. Okay, now you do not have any grid, but maybe it's not so easy to see now how the solid looks like. Okay, so you can also do all kinds of changes. Okay, if you do not like the way Maple initially plots the solid, you can also change here the colors and so on and so forth. Okay, so we have all kinds of possibilities, and all those possible changes can be easily. You can, if you're not sure how to do it, just use something like this here, so, and you get all the possible options you have. You can specify for doing a plot. More or less, for implicit plot, you have the same comments, and you see you can introduce labelings. You can tell Maple to use a different grid style. You can write things on the plot, and so on and so forth. So you have all kinds of possibilities. I think it's even possible to. I'm not sure whether I have options here. The most easiest thing is you can do it directly here. So you can click on the right button, and then you can do here all kinds of stuff. So actually, I can do it already here without doing the command. So it's maybe more easy. Then you do not have to memorize, okay, which comment do you need. But you have to tell Maple that your surface is given in cylindrical coordinates. This is what you have to tell. And they have to be careful about the order in which you write here the ranges. Even so, if you call it theta and set, if you interchange it, okay, of course, even so it's for you theta and set. It's not for Maple, okay, because for Maple, of course, the order is important. Okay, so we will see some more examples in a few minutes. So last time we already started to discuss so-called space curves. Which are as the name suggests, curves in the space. Now we have two different kinds, two different ways in order to give such a curve. One is by parametric equations, which is then similar to what we have discussed last semester in the plane when we discussed parametric curves given by parametric equations. So you can either specify a space curve by parametric equations. Normally what we assume is that f, g, and h are all continuous functions. Or what is, or an equivalent way is you just give a vector function. Okay, and then the meaning is that the curve is traced out by the tips, by the endpoints of the vector function here. So we have two different ways in order to describe a space curve. Now, last time we started already to discuss some examples. The example which I showed you last time is this one. Cosine ti plus sine tj plus t k. Okay, this is a so-called helix. Okay, and I already discussed, okay, how if you have given such a space curve, how to plot it. So for this, in this example, sometimes it's the most easiest way is you identify a surface on which you first identify a surface on which the space curve is contained. Okay, then you have already a better feeling where the space curve is located, and then you try to figure out how the curve on this surface looks like. Here, this is one example because you see that if I look at the parametric equations, you see that x squared plus y squared is equal to 1. So the helix must be contained on a cylinder. And this helps you already pretty well to understand how the helix looks like. So what you are going to do then is, okay, you plot a cylinder. Okay, and we know that because of this, we know that the helix, the space curve, is on the cylinder. And now we look at this at the point t is equal to 0, which is here. So you start, in some sense, you start here, and then if you look at the curve from above, okay, it just goes around the circle, but at the same time it moves upwards if t is getting larger. So what you have is something like this here, and so on. Okay, so this is one way. If you do not have access to a good graphing, to a software like Maple, then this is one way how you can figure out how a space curve looks like here. Another example of the same spirit would be the following one. So for instance, this one, so x is equal to t times cosine of t, y is equal to t times sine of t, and z is equal to t. Okay, so you see immediately from the equations that x squared plus y squared is equal to z squared, which means that this space curve is contained on the cone. Okay, so you have the cone. And you see again, as t is getting larger and larger, you're always on the cone, okay? But as t is getting larger and larger, at the same time, you're moving up, okay? So you have something similar, but on the cone. Okay, so you move something like, and then you move something, and so on. And this is the direction, okay? And the same in the negative direction. So you see, this helps you already pretty well to understand how such a surface looks like. Another example would be the following one. This one. Which our textbook calls twisted cube. Okay, so here you see that, again, the parametric equations, x is equal to t, y is equal to t squared, z is equal to t to the cube. Okay, so you see that because of this relation, you see y is equal to x squared. Okay, so this space curve is contained on the parabolic cylinder. Okay, so you have here this cylinder. Okay, so you see that because of this relation here, our space curve must be on this parabolic cylinder, and as t is getting larger, you start here, and as t is getting larger and larger, the z is getting larger and larger. As t is getting smaller and smaller, the z is getting smaller and smaller. Okay, so you kind of move up here. Okay, and the same in the other direction. So here you move down. So you go something like always on the. Sorry, this should be. You have behind also the. I'm not very good in drawing something like this. You have behind also the parabolic cylinder. So you go something like this here. Another way to plot this, okay, would be, but maybe more complicated, would be okay to first to observe that our space curve also is on this surface here. Okay, so our space curve is contained in this and this surface. So you can draw the intersection of those two surfaces, but maybe not so easy to draw. Okay, so this surface is this here, and this surface would be the same, like this here, the cylinder generated by this space curve here. Okay, projected on the ZX plane. Okay, so that this would be the this surface, and you can roughly imagine how this looks like. Of course, something like this, the intersection of two surfaces and so on, everything is possible to draw with Maple. But it's much easier to directly draw space curves, and Maple is able to do this. So normally, because for such examples, it's quite easy to figure out how they look like. But if I give you a much more complicated example, for instance, this one, x is equal to 2 plus cosine 1.5 t cosine of t, y is equal to 2 plus cosine 1.5 t sine of t, z is equal to sine of 1.5 t. Okay, without having access to a program like Maple, it would be very complicated to figure out how this space curve looks like. Another example is this one. X is equal to square root of 1 minus 0.25 cosine square of 10t cosine t. Y is equal to square root of 1 minus 0.25 cosine square of 10t sine of t, and z is equal to 0.5 cosine of 10t. Also for this one, it wouldn't be too easy to figure out how this space curve looks like. But here you observe something. You observe that x squared plus y squared plus z squared is equal to 1. So at least you know that this space curve is on the sphere. Okay. But again, for knowing this, not very helpful. Okay, but at least you understand roughly where the space curve is located. Whereas here, it's not so easy. You do not have any clue. Okay, and for this, you really need a program like Maple. So I showed you already that you can use these with plots get a couple of new comments, and you see one of them is called space curve. Okay, so the space curve comment will be the one to plot space curves. Okay, so let's maybe first take a look at the syntax. So space curve. Okay, so here you see how to use the comments. Okay, so here you see that this is the way how you specify. So you give Maple the space curve, the 3 component functions, and then the range over which Maple should plot it. Okay, so maybe let's first check this example over there. Okay, so space curve. Now 2 plus cosine 1.5 times t times cosine of t, 2 plus cosine 1.5 times t times sine of t, and sine of 1.5 times t. Now I have to specify t, so t from 0 to, if I go to 2 pi, this is not enough, then I do not get, because this is symmetric, so I should go to 4 pi. I forgot the bracket. Okay, so you get something like this here. I should more points, because you see this doesn't look too pretty, so more points. I'm not sure whether 1000 is too much. That's 500. Okay, now it looks slightly more pretty, so 1000 will do it. Okay. So you see that even so, if you have a graving device, okay, or even if you're able to plot this, okay, on the blackboard, okay, this is not very useful because from this you do not understand, okay, like if you look at the point of intersection, okay, does the space curve really intersect there, or is one point higher than the other one, or one point in front of the other one? Okay, so it's not really clear. Okay, so it's very important for space curve that you are able to look at space curve from different directions. This in Maple, as I told you, is easy because you can rotate it. But maybe it's even better if you enclose the whole thing in a box. Okay, then it looks maybe then it's more easy to grasp. Okay, what are the differences? So this you can do. You can say, okay, the axis should be boxed. Okay, so this is maybe more. This is maybe better to understand. Okay, how this curve looks like, and now again you can change your viewing angle, so you can look at it from different directions, and you can try to understand properties of this very strange curve. Okay, so but without having access to a graving device, maybe you will agree it wouldn't be possible to understand how this space curve looks like here. I guess it's if it is not possible to see very clearly, I guess there is also line style. No. There are some options, but I would have to check it. So if this is not plotted thick enough, you can tell Maple to choose a thicker line style, and then maybe it's easier to understand how the space curve looks like. Okay, let's look maybe at the other example. So the other one is, we have also times cosine. So this we can keep. And here we have the square root of 1 minus 0.25 times the cosine of 10 times t squared times cosine of t. And here we have the square root of 1 minus 0.25 times cosine square cosine 10 times t square times sine of t, and here we have 0.5. 0.5 times cosine 10t. And here actually the period is it's enough. If I go from 0 to 2 pi, then I get the whole curve. Because otherwise it's just repeating. Okay, so you see that. Okay, so you have this one. And you see that. It looks a little bit strange. It doesn't look like it's contained on the. It should be like this, maybe. What are they? Okay. This is because of the because you see this the axes are scaled differently. That's why it looks so strange. Because I just thought because we easily see that this surface should be on the sphere. It doesn't really look like it's on the sphere, unit sphere, but this is because the axes are differently scaled. Okay, so that's why it looks so strange. But actually, you could also use Maple to plot a sphere, and on the sphere you can plot the space curve. Okay, I'm not going to show you because this needs some more research into Maple, the plotting comment. Okay, but it's possible to plot the sphere first, and then you plot this on the sphere. Even you can because now you see I plotted it immediately. Even you can tell Maple the parameter t should slowly grow from 0 to 2 pi. Then you get the sphere, and then you see how the curve is slowly traced out. Okay, even such animations are possible with Maple. So you have all kinds of possibilities in order to understand how space curves looks like. Here you see a good strategy sometimes for space curve is, of course, here it would be nice to plot it on the sphere, okay, because then you would get a better feeling how the space curve looks like. But another good way is to plot it inside the box, because if you do not plot the box, then you see it's like it's maybe less clear, okay, how the space curve looks like. Okay, so one strategy is to plot it into a box. Another strategy would be to plot it inside a tube. So you have a very tiny tube around the space curve. Sometimes very helpful in order to understand how a space curve looks like. Let's look at another example. Then I show you how to do this, how to plot it in a tube. So you find in our textbook also this one. This space curve. T minus sine of t, 1 minus cosine of t, and t, where t is from, let's say, 0 to 6 pi. Okay, so you have this one. It's gone. Okay, so this may be not very clear how it looks like, but you have another. You see, for something like this, it's sometimes good. Even if I put it in a box, it's not clear how this looks like. But you have another comment which is called tube plot. Okay, tube plot encloses the space curve inside the tube. Okay. So let's check. The syntax should be the same. Let's first check it. Tube plot. So help tube plot. Okay, so again, this is for a space curve. So you see here the syntax, and you also have to give the radius of the tube. Okay, so this is the last parameter, it's the radius of the tube. Now, if you do not understand what I mean by a tube, you will see it in a minute. So okay, we replace space curve by tube plot. We can use the same syntax, and we have what was the third one? Radius, right? Radius is equal to 0.5. This is not good. This tube is too thick. This is maybe better, but the color, I do not like the color. yeah. Why is it always gone? Ah, okay. So it doesn't really look like there is a tube around it, but maybe let's change the color. No coloring. What is this here? Color. Default, no lightning. I'm not sure what I can change here, but so let's just do the color. Is equal to, let's choose blue. No effect. This actually doesn't look like the plot I wanted to have. So let's tube plot. Maybe I should remove the number of points because it seems to have a different meaning because I have also a tube points, whatever this is supposed to be. Okay, so let's remove the now it's better, but gone. I'm not sure how to place it, but you see now it's or maybe let's make this slightly larger. This is too large. It shouldn't look that flat. This is what surprises me. So maybe like this here. Okay, maybe something like this here. You see, this kind of curve looks a little bit similar to this is not the best way to. Looks a little bit similar to what we called last semester the cycloid, but the cycloid was something like this here. Okay, so the cycloid is the curve. If the curve is the curve which is traced out by a point, which is on a sphere. So you have a ball, and you let it roll. You mark a point on the ball, and the curve which is traced down, the plane curve which is traced out by the point is called the cycloid. This is similar, but the cycloid just because you have also the you have also a parameter for the z direction. So the cycloid is not just moving like this here, but also moving up at the same time, and also moving in the space. So something like this here. Okay, so this is not really. So let's maybe plot the other one. Maybe the other one looks more convincing. T minus 3/2. This is somehow similar to the okay, similar. Yeah, but this is kind of. Of course, it would also maybe it would be also good to understand what are the coordinate axes. So I can also add the axis. I guess this works. I'm not sure. I never have done it for the tube plot, but okay, this also works. So then you understand more how the curve moves up and so on. So you see that looking at these examples, you see that Maple is very powerful in plotting curves like this. And if you really want to understand space curves, then you certainly need to have access to a program like Maple. Okay, so any questions to this? You see, it's also very easy to use because you see me, I'm learning at the same time while I'm doing it. I'm not very familiar, I'm not doing it very often because I'm doing other things with Maple, but you just need 5 minutes and you can figure out how to plot things. So it's also very easy to use. Okay, so in this section, section 13.1 in our textbook, we introduced vector functions and the space curves you just seen, in some sense the graph of a vector function. Now what we want to do is, because we also already introduced the limit of a vector function, which we just defined pointwise. We also introduced a vector function is continuous. What is the meaning of this notation? Again, we just used the usual notation from the usual definition from last semester. In other words, we just define it component-wise. So a vector function is called continuous if every component function is continuous. Now the next thing we want to introduce is the derivative, differentiability. So a vector function is called differentiable at some point t is equal to t0 if okay, so actually we can use the same definition as last semester. So we we try to look at this number here, which is the limit t tends to t0, and then r of t minus r of t0 over t minus t0. If this limit here exists, then we will say that the vector function is differentiable at a point. Okay, so this is, we just take the same definition as the definition we have seen last semester. Notice that, of course, what we look at here is a vector. So we have a vector here, and the product here was 1 over t minus t0 is the scalar product of vectors. And we defined last time what the limit of a quantity like this, because it's a vector function, what the limit of a vector function is supposed to mean. You just take it component-wise. Now, what is the meaning of this number here? This is easy to visualize. So if you have, if this is our coordinate system, and assume that the function, the space curve, which is traced out by the tips of the vector function, is given like something like this here. Okay, then at the point t0, okay, we have here a certain position vector. So, for instance, let's say this is the position vector r of t0. Now, if we look at this expression here, okay, so here what we do is we have another position vector r of t, okay, and we know that this vector here is given by this vector. Okay, so you see that if this limit exists here, okay, the meaning of this limit should be at this point here, t0, a vector which is tangential to this point here, to the curve at this point, and points in the direction of the curve. Okay, so this is the meaning of this symbol. Okay, so you see this from here. But of course, we haven't defined the tangent for such a space curve. Okay, so we are going first. We first define this one, then using this we can define the tangent, namely the tangent to this point here of the space curve C is defined as the line which passes through this point, and as direction has this derivative here. Okay, so only if the derivative exists we can talk about the tangent. Okay, so we first define the derivative and then we define the tangent. Okay, so the tangent to this, let's say this curve is C, to C at the tip of r of t0 is defined as the line which passes through the tip and has direction given by the derivative. Okay, but you see that except of a direction, okay, this vector here has a length as well, and because most of the time we are just interested in the direction, not in the length. So we will most of the time we will normalize it. So we will divide it by its length, and this normalized vector is denoted by this symbol here. So this is the derivative at t over the length of the derivative is called the unit tangent vector. But it's not necessary that the unit tangent vector exists, okay, because it depends. If the derivative exists, okay, and it's not equal to 0, then the unit tangent vector exists, okay, because the derivative can also be equal to 0. And such curves where the derivative exists but is not equal to 0 is called a smooth curve, smooth space curve. Now, you see already from this definition, which I gave, this limit, t tends to t0, okay, if we introduce coordinates, okay, so if we say that, that this vector has component functions f of t, g of t, and h of t, okay, then we see this, that this is the limit t tends to t0, and then here we have okay, f of t minus f of t0 over t minus t0, and here we have g of t minus g of t0 over t minus t0, and here we have h of t minus h of t0 over t minus t0. And the limit, by definition, is component-wise, so we can write the limit like inside the vector for every component. So we have this limit f of t minus f of t0 over t minus t0. The limit t tends to t0, g of t minus g of t0 over t minus t0, and the limit h of t minus h of t0 over t minus t0. Okay, so this means that a vector function is differentiable at t0 if and only if all three component functions are differentiable at t0, and we can compute the derivative just as the derivative of the, just by looking at the component functions and taking the usual derivative, which we have discussed last semester for the component functions, and considering this vector function here. Okay, so a vector function is differentiable if and only if all the component functions are differentiable, and the derivative is given by this easy rule here. Okay, so once more, the reason why we discussed the derivative is more or less the same reason why we have discussed the derivative last semester, because we can use the derivative in order to define the tangent. You also find this definition, the definition I already mentioned in our textbook, namely a space curve is called smooth on some interval, okay, on some domain, if the derivative exists and is not equal to 0. Okay. The reason for this notation is so like in last semester we called the curve smooth if the derivative exists and is continuous. Okay. Here a little bit different. The curve is called, the vector function is called smooth if the derivative exists and is not equal to 0, because in this case smooth space curves have a unit tangent vector in every point. Okay, that's the reason. You see that, for instance, if we look at this example, the twisted cube. Okay, then you see that the derivative. So the derivative is very easy to compute here, just component-wise: 1, 2t, 3t square. Okay, the derivative is always not equal to 0, so this function will be smooth everywhere. If you look at this function here, let's say 1 plus t square, let's say t to the cube, let's say 1 plus t to the fourth. You see this is just defined for t is larger or equal than 0, so the domain of this function will be t is larger or equal than 0. And if you take the derivatives, actually this is not good, because let's say here we have a t. Okay, then we have 1 plus 2t. Also, this will not be good enough to make it smooth. Wait, I have to check which example. I think in our textbook it's 1 plus t to the cube and t squared, something like this. Yeah, 1 plus t. This is a good example, t squared. So this actually is a plane curve. It's not a space curve, but you have the same definition. Okay, so for the derivative, you will have 3t squared and 2t. Okay, and you see that this will be equal to 0 for the 0 vector, actually, for t is equal to 0. Okay, and indeed, if you plot this curve, but actually, sorry, I thought this. I just thought this is a square. Actually, for t, this of course is defined for all t. Sorry, this is of course defined for all t. I don't know why I thought t must be larger or equal than 0. Just for a minute I thought this is the square root. Okay, so of course this is defined for all t, this space function, and you see that there is one point where the derivative is equal to 0, namely t is equal to 0. Actually, if you plot this function, it looks like this here. So you see that the point where the where the plane curve in this case is considered to be not smooth is this point here. But if you exclude this point, then the space curve will be smooth for the other. So if you just look at the domain, which is t is larger than 0 or t is smaller than 0, it always will be smooth. So if you can divide the domain into subsets such that the vector function is smooth on all those subsets, we will call the original vector function piecewise smooth. So piecewise smooth is smooth except you have a finite number of exceptions. So something like here, you have only one exception, t is equal to 0, where this function is not smooth. Okay, and if you look at the graph, this of course is something you would consider to be, so such a point you would consider to be not smooth. Okay, but the derivative here is equal to 0. It's not that the derivative does not exist. Okay. So if you look at this function as a vector function using this way to express this function as a vector function, then the derivative at t is equal to 0 indeed exists. Okay, but if you look at the graph, it looks like the derivative does not exist. If you look, if you consider the derivative in the usual sense. Okay, that's why we have exclude here all the points where the derivative is equal to 0, because in this case you do not get a direction. Okay, because the derivative should have the meaning of the direction of the tangent. But if the derivative is equal to 0, okay, of course the derivative in our new sense exists. Okay, but you do not have a direction for the tangent. Okay, that's something we want to exclude. That's why a space curve is called smooth if the derivative exists, but it's not equal to 0. It's a little bit different to what we have seen last semester. Now, you find in our textbook a couple of properties which are satisfied by the derivative of a vector function. So in particular, you have all those laws you would expect. So maybe I copy some of them on the blackboards. So the first one is, okay, if you consider the derivative of a sum of two vector functions, then of course this is equal to the derivative of the sum the same, of course, is true for the difference. The same is true for the scalar product. So if you have the scalar product of c times a vector function, this is just c times the derivative of the vector function. Now, as for the product rule holds in for a couple of situations, because actually for vectors we have different kinds of products. So we can the first product we can consider is the scalar product of a function times vector function. So for this situation, you have here, this is the usual derivative times u of t, scalar product plus f of t times, and now you have our new derivative of the vector function. And the same holds true if you replace, if you replace this here by another vector function and interpret this as a dot product. So if you have a dot product, then you have the same rule. So this is the derivative of u of t times, and this here is now the dot product. This is the scalar product, v of t plus u of t times the derivative of v of t. And the same is true if you replace here the dot product by the vector product. Then also you have the same rule. Okay, so the rules which we are used to also extend here to the dot product and the cross product of two given vector functions. And of course you have something like the chain rule. So if you plug f of t, some function, into a vector function, then what you get is the usual derivative. Our new derivative of the vector function evaluated at f of t times the usual derivative. And you see, of course, the proof of all those trivial, because everything is just you do it component-wise. So what you do is you introduce the component functions, okay, and you write this out. Because here, for instance, like this sum here is defined component-wise. The derivative is defined component-wise, okay. So you get this rule immediately from doing everything on the level of, so you introduce the component functions and use them, and because more or less everything, not this one and this one, they are not defined component-wise, but for the other ones, it's immediately clear that those laws should hold. And here you just introduce component functions and verify that the right-hand side and the left-hand side are the same. So this is not complicated. I just want to emphasize that having those rules. Okay, it's becomes very easy to prove certain properties. So, for instance, if you have given that the length of a given vector function is a constant, then and you have to show that this implies that those two vectors here, so the original vector function and the derivative are always orthogonal. So the most easiest way to show this is to realize that, okay, so this means that that the dot product of R of t with itself is equal to c squared. Okay, now you differentiate both sides. So what you get is you can use this rule here, the product rule. So if we take the derivative here, okay, what we have is twice the derivative of r, the dot product with R of t is equal to 0. Okay, so what you get is that the derivative of R of t times the dot product with R of t is equal to 0. Okay, and this already shows that this is satisfied here. So you see now the advantage of having defined the derivative of vector functions like this and having such rules is that we can now prove something like this here just by doing calculus. Of course, this is something which is clear because this means that the tips are all located on a sphere. Okay, and this is a property which we know that if you look at the vector, so this is the vector which points at the sphere. Okay, and this is the tangent. Okay, and they must be orthogonal. Okay, this is something which we also can see geometrically, but you see what the difference is here. I do not have to look at this from a geometric point of view. I still, just by using calculus, okay, straightforwardly can prove that those two vectors must be orthogonal. And this is the real advantage of introducing this notation. Next time I will finish this, and then I will go on and discuss the curvature. And the final thing which I will do is to convince you that this approach is really introducing derivatives and then also integrals for vector functions is really useful. You have seen this already in physics, but in our textbook there is a proof of one of Kepler's law of planetary motion, and this is what I introduce, what I will do next time. Then you will see that once you have developed calculus for vector functions, a proof of the Kepler's law of planetary motion are quite standard, and you do not have to do any experiments. It's just a matter of calculus then to derive that the well-known fact that the Earth is rotating around the Sun in an ellipse. Okay, so any questions? If not, then that's it.